Hi class, we are on the last section of chapter 2, a numerical method. So today we're going to cover, again, this is considered review. This is something that you would have seen in a Calculus 2 class as well, in the differential equation section of Calc 2, right after you go through your integrations. So we're not going to go through it quickly because even when I teach Calc 2, this seems to be a section that's kind of difficult. So numerical methods they're really just that. They're methods that go through, there's algebra incorporated, but it's really all about approximation. So these are methods that are used a lot by engineers and also by physicists, right? So they're used to make approximations. Okay, so numerical methods, generally in a math degree, an undergrad math degree at that, you would take 2 courses called numerical methods, generally in numerical methods 1, numerical methods 2, right? So numerical methods, they're not limited to only differential equations. You use them in a variety of things. Basically, it's the study of approximations and errors, okay? So we're going to talk about the simplest numerical method that we have right now for DEs. Later on in the course, in chapter 9, I believe, we cover several numerical methods, right? So, and when I say several, I mean a couple, a handful, the most used. There's several different numerical methods, so we're going to go over them now. Another numerical method that you've probably been exposed to would have been in Calculus 1, which is Newton's method for finding the zeros of a polynomial, right? So that's another example of a numerical method, okay? So let's go ahead and get started. Numerical methods are definitely something that are eased by computers. So whenever you run a numerical method, you generally would use some sort of technology, computer program. You would generally program your computer to run a numerical method, okay? So as we said, some DEs cannot be solved by the methods we've covered so far. So the equations are not separable. They're not linear, or they can't be solved with an integrating factor. They're not exact. Substitutions aren't going to work. There's a variety of equations that are non-solvable, right? So when we approach a non-solvable question, what we do is we try to approximate their solution by using a numerical method, right? Maybe for these unsolvable equations that we have, looking at the directions fields like we did in 2.1, I believe, is not going to give us enough information for analysis. Maybe I need to have actual values, or I need to really be able to look at some values, right? So what we're going to do then is we would look at numerical methods, okay? So this will allow us to have a deeper analysis of what the solutions look like and how to manipulate them, right? So numerical methods allow us to get an approximation of values to a solution curve, right? So there are several numerical methods, as I said before, but for the moment we're only going to focus on one, which is Euler's method. Okay, this is not Euler, it's Euler, right? It's common to mispronounce his name. Very, very, very famous mathematician. There's lots of things with Euler's name attached to them. He was very, very smart up until his later years of his life, which is not common for mathematicians, actually. So let's go over Euler's method. So when we do this, we're really going to run through the method as an exploration rather than, hey, here's the formula, right? So his method is very, very algorithmic. We're actually going to develop this algorithm through an example, okay? And we'll kind of go through it through a plain sense method, right? And then through this plain sense method, from what we know through calculus, we will develop his algorithm, right? So let's go ahead and get started. All right, so we have this IVP, we have this equation, right? The first derivative is equal to y plus x times y, and we have y of 0 equals 1, right? So I have an initial condition. Note that this equation is separable, okay? Now I chose a separable equation on purpose so that we can compare our approximation that we're going to come up with versus the actual solution, right? So it's nice when we have this, but obviously we always, like I said before, have something that we can find the actual solution for. So we're doing this here just for exploration. We're going to do something that we can actually look at, right? However, the process is the same whether or not we can find the solution or not, so it doesn't really matter. Okay. So what we want to do first is we want to take this point that we have and we want to plug it into our DE, and we want to find the slope at this point. Very much so like when we're trying to create a slope field or a direction field, right? So I'm going to take my point. I can extrapolate that x is 0, right, and y is 1 from this point. And if I plug it into my DE, right, plugging in 0, or 0, 1, really, I'm going to get 1 plus 0 times 1, which gives me out a value of 1. So that what that means is at this point, 0, 1, my solution has a slope of 1. Okay, so a solution curve to this IVP has a slope of 1 at the point 0, 1. So now how do we use this information? I have a point and I have a slope. Well, normally in an algebra class, if I give you a point and a slope at that point, or a rate of change, you can come up with a linear function, right? An equation of a line. So that's exactly what we're going to do. We're going to come up with the equation of a line at this point, centered at this point, I guess I should say, with the slope of 1. And that will be an approximation to our curve at that point, right? It'll be a linear approximation, right? So we're doing, basically, we're linearizing, not linearizing, we're making a linear approximation that works close to our question at hand, but doesn't work far away from our question at hand, right? Our equation that we have. So the linear approximation with this slope is the line L1, which equals x plus 1. And that should be very, very easy for you to see because this is a y-intercept. So my b equals 1. And the slope is 1. So it's very easy to throw that in together. I don't even have to do any math to come up with that equation. Now we're going to do this basically over and over again, okay? I prefer the equation y equals mx plus b because it tells you what your y-intercept is and it tells you your slope. It's useful for everything. I see a lot of students that like to use the point slope form. The y minus y naught equals m times x minus x naught. That equation is trash. Please don't ever use that in my class, okay? All that is the lazy person's form of the equation of a line, right? That literally doesn't give you any kind of information except for a point and a slope. It's not hard to find the equation of a line from that. Please don't give that to me. It's not going to be useful for what we're doing in this class for right now or at any point thereof, right? So please don't use that. Please use the form y equals mx plus b. I really don't think I should have to say that, right? But it does come up when I see work. So this is the equation that's going to be useful for us. So that's what we're going to use, right? So this approximation is going to be good close to this point 0, 1, right? But it's going to diverge rather quickly from the actual solution curve for x because it's very clear here that whatever solution I get, it's not going to be linear, right? If I take the first derivative of something and I end up with a multivariable function here, there's no way that I started off with a linear equation, right? The derivative of a linear equation is a constant. This is not a constant, so my solution is going to be some sort of a curve. And so since I know that my linear approximation close to this point that I have, this initial condition that I have, is going to work close, but it's going to quickly diverge because I'm approximating a curve with a line, right? So what we need to do then is we need to make an adjustment, okay? I'm basically going to create a second linear approximation at the end of this linear approximation. Okay, so I'm going to say that basically my linear approximation is okay up to some point, and then after that, it diverges from my actual curve quite a bit, so I'm going to make a correction to the course of my approximation by creating another line, okay? So we're going to use our line here to acquire another point to plug into our DE and find the slope at that new point, okay? So this is what we have so far. This is the actual solution curve, okay, which we'll talk about at the end of this video. And this is my linear approximation. So obviously it's a tangent line, so it works at that point. But after I get a little bit away, right, in this case 2 units, the difference in my output values is extremely large, right? Even when I'm 1 unit away, it looks like the difference is more than 2 units away, which is a huge error basically, right? So what I want to do is I want to pick a point that is close so that the error is not too far off. And then what I'm going to do is I'm going to look at the slope at that point according to my equation that I have, or the slope in the slope field that would be generated by this equation. And I'm going to correct my line, and I'm going to draw a new line that has that slope, right? And I'm really just going to repeat this process. So in that way, what I'm going to do is I'm going to come up with several linear equations that will approximate this curve. So it's going to look like a choppy set of lines that are attached to each other that basically just correct themselves at a certain distance away from, you know, my initial point, so that it can try to hug my curve as close as possible. So we outline what we're going to do, right? So I have this point, I have this slope, I created this line as a linear approximation. So what I want to do is I want to step a little bit away from the point that I'm at, okay? We'll call this distance that I move away from my initial point a distance of h. Okay, we call that the step size. That's why I want to step away from my initial point, right? Here, let's say that my step size is 0.1. So if I'm at 0, I'm going to look at what is happening at 0.1. After I look at what's happening at 0.1, I'll move another 0.1 away, and I'll look at what's happening at 0.2. Then I'll look at what's happening at 0.3, then 0.4, then 0.5, etc., etc. I'm always going to use this as a standard distance, okay? Now the step size, generally when we are given these problems, the step size will be given to us, right? They'll say use a step size of 1. Use a step size of 1/2, 0.5. Use a step size of 0.2, right? They'll tell you what the step size is. Okay, so our new input we're going to have is our old input plus the step size, right? So that's 0 plus 0.1, which gets me 0.1. So I'm going to plug that into my line that I created as a linear approximation, because at this point, remember, I don't have an actual solution curve, right? I can't just plug this point into my curve and see what I have, because I don't know this. I showed it here just so you can see what this looks like, but really at this point all I have is a linear approximation. All I have is this line, okay? So I know that at this point this line approximates my curve, right? So if this picture of the red solution curve was not here, all we would have is this line. So then what I want to do is, to make my adjustment, is I move up a little bit and I evaluate my point on that line so that I have an output, right? So I know that at 0.1, I have the point 1.1 on this line. Okay, so I find a new point on my line, right? So now that I have a new point on my line, I'm going to plug that point into my DE that I have to find the slope at that point, right? Because remember, there's a slope field here that's generated by this curve, by this equation that we're looking at, right? So I want to know what is the slope at this point. So I'm going to take this point, right, that is a little bit down the line on my linear approximation, right? So it's still pretty good approximation to this curve that I actually don't have. And I'm going to plug it into my DE. So I'm going to have y plus x times y, right? That's my DE. And it's going to tell me that the slope is 1.21. So at this point, I have a slope of 1.21. So as I go down my line a little bit, in the field, the slope field or directional field that's generated by my DE, the slope here would be 1.21, slightly larger than what it is for my linear approximation, which makes sense, right? So at my next point, I should have a linear approximation that is slightly more increasing than the linear approximation I have at this point. So I'm going to do the exact same thing I did before. I'm going to find the equation of the line that contains this slope and has this point. Okay. So I'm going to find my next linear approximation. I'm going to call it L2 because L1 was the first approximation. So for L2, we're going to have y equals mx plus b, where I'm going to plug all that in. I have x, I have y, I have my slope m. So I'm just plugging in. I find my value of b. Once I have b, I can throw that together to find L2, right? L2 is equals mx plus b, right? So this is the slope at this point. So now that I have a new linear approximation, I do the same thing. I move over just a little bit, right? And I find my next input, which is going to be 0.1 more than 0.1. So I'm going to plug in 0.2 here, get my output, take that output, plug it into my DE to find the slope at that point, and then use that xy and the slope that I have to find the next linear approximation, L3. Okay. So for our next approximation, we need the next point. So x2 is x1 plus h, which is 0.1 plus 0.1 or 0.2. Very easy. We actually don't have to calculate. We're just counting by 0.1s at this point. I plug that into my second linear approximation. Okay, so I'm just plugging in 0.2, and I'm going to get out my new slope. Now, I want to talk about this now. We'll talk about it later also. Don't round, okay? Never, ever, ever round when you're doing a linear approximation. You need as many decimal points of accuracy as you can get, right? If you start rounding to the first decimal point, you've completely negated the whole purpose of using a linear approximation, okay? So numerical methods, you try to keep as many decimal points of accuracy as you can, right? So here I have my 1.221. That is the point. So when I plug in 0.2, I get out the point 1.221. So that is my next point. Okay. So now I need to take this input 0.2 and 1.221 and plug it into my DE, right? So this is the output for the approximation to my solution at 0.2, right? My linear approximation is 1.221 at 0.2 to this. Okay. So what I'm going to do is, well, I guess this is what we have, right? So again, I don't actually have a solution curve at this point because most times the solutions are impossible to find. That's why we're using the numerical method. But I have my x naught. I have a linear approximation, but only up to a certain point. Okay. And then at that point, I now need to make a corrective course, and I'm going to do another linear approximation. Okay. And then I would do this again for the next iteration, right? So right now, this is my approximate output to my DE solution, right? This y2, right? This 0 to 1.221, this is my approximation to the solution for this DE with this initial condition at this point. Now, obviously, it's not exact because it's an approximation, right? But this is what my approximate output is, 1.221, right? That's the best I can get from what I have. So if we continue this process, we're going to get an approximation curve, okay, which would look like this. So again, here I graphed our approximate solution, right, our numerical method solution against our actual solution, which we don't have, right? But you can see that it's rather close, right? It's relatively close until you start to get pretty far away, right? So as you can see, the error starts to grow as you get further and further down in your iterations, okay? And we have other methods that, you know, come back and correct those. But for right now, that's the process, right? So I have a linear approximation, I make some sort of corrective adjustment, and I create a new linear approximation. I make some sort of corrective adjustment, and I get a new linear approximation. And I just keep following that. And then what happens is I start to approximate my curve with several linear approximations. Okay. And again, there's obviously error, that grows as we move further down the line. Okay. So we can see that our approximation begins to diverge from the actual solution curve the more iterations that we have. The smaller the step size we have, the more accurate we're going to be to our actual solution curve, right? So if we had a large step size, right? So for instance, if I was going a full unit away each time, my approximation curve is going to be probably useless after the second iteration, right? So we want to keep our h small, right? The smaller the better. Obviously, if h is too small, it takes a lot of computing power. It takes a lot of time. It might not be very useful, right? So you always want to compare processing power and computation time versus usefulness of your approximation. So luckily, we have methods of looking at the error from our approximation. A lot of times that's a whole, well, in a numerical methods course, that's a big part of your course, which is your error approximations, right? Your error analysis. So from our last calculation we had the input 0.2 and output 1.221 for the approximation from this L2 line that we had. Okay. So notice here that 1.221 can be written in terms of my step size, 0.1. So if I were to do that, notice that my output is me plugging in 0.2 to my linear approximation, right? So when I plugged in 0.2 to my output, that's how I got out 1.221, okay? However, I know that 0.2 is just 2 iterations of my step size, okay? But also note that 0.979 came from me plugging in 0.1 into my y equals mx plus b form of L2, right? So let's come back here, right? So when I found 0.979, I plugged in 0.1 into y equals mx plus b from my first iteration, right? And even 1.21 itself is some form of 0.1. There's always a 0.1. This step size it keeps showing up, right? It keeps showing up, it keeps showing up. So if we go through this little derivation that I'm trying to show you here, okay? And apologies, this should be at 1.1. I'm not going to fix this now because I'm lazy, but I will fix this in the write-up for those in my class. So this is not a three variable input. It's just one, or I'm sorry, it's just two. I just have an error here. Okay, so I plug in 0.1 and 1.1 into here for my L2. So if I'm looking at what 0.979 is, it was 1.1 minus 1.21 times my 0.1 term, right? As I just showed you when we went backwards. So I have that 1.221, right? I'm taking this thing here. This part stays the same. And I'm replacing how I found here into my equation, all right? I found that by using y equals mx plus b on my, let's come back here real fast. I know we're jumping around a lot. On this equation here that we had, right? So I had y equals mx plus b, and that's how I found 0.9779. So in order to find b, what I did was I took this and I subtracted from it 1.21 times 0.1. And that's how I get 0.979, right? You isolate b. So notice what I have when I go back is 1.1 minus 1.21 times 0.1. Okay. 1.1 minus 1.21 times 0.1. That's how I found this. So I'm going to replace that with the math that I had from that L1 equation. So we have 1.21 is this part that I'm just bringing down, and my substitution for 0.979. Okay. Now notice that I have 0.1 here, I have 0.1 here. Okay. So I can move those together and factor out the 1.1, and I'll be left with 2 minus, there's just 1 here, right? I have a common factor of 1.21 and 0.1, right? So that reduces to 1, and I just have 1.1 plus 0.1 times 1.21, right? So I'm moving these around in a way that's beneficial for me to derive an equation. So another way of looking at this then is going to be my second approximation is equal to my first approximation, 1.1, plus my step size times the slope that I get when I plugged in my previous input 0.1 and 1.1 into my DE, right? So y1 is the previous solution approximation that I had. y2 is my current solution approximation. And y prime of 1 is the slope of the previous linear approximation, right? So to generalize this, we get my next approximation is equal to my previous approximation plus my step size times the slope at my previous approximation, or my current approximation, we could say, right? Or if we extend this a little bit, right? Y prime, where I'm plugging in xn and yn into my y prime. So xn and yn is the step that I'm on. This is my next output, right? So let's use this formula that I have now from scratch. This is the actual Euler's formula, right? Euler's method formula. So let's do this from scratch from the beginning problem, and we'll see that we get the same things out, okay? So here, I want to find an approximation for y equals, for my solution curve at x equals 0.5. So I need 5 steps, okay? We've done 2. I need to do 5, right? So this is my equation. This is my initial condition, and this is my initial step size. So following the same process that we had before, we're going to keep 9 decimals of accuracy, right? Ideally, we try to keep as many as we can. So let's do this in a table. It'll be way easier to do it in a table. So for our first step, our initialization, we have x of 0 and y0, right? X naught, y naught of 0, 1. Okay. So here my step is 0, right? This is step 0. I should have made another column here, I guess, for the step that we're on. So this is not step 1, it's step 0, right? We're starting off here. That's my initial step. So when I plug in x0, y0 into my equation here that I have to find the slope, it's 1 plus 0 times 1, which we've done already. We know that that's going to be 1. And then when I plug this into my formula for y1, right? Because this is x0, y0. So in order to get y1, right, my first approximation, I'm just going to plug that in here, right? So yn, or y0 is 1. My step size is this. And the slope at that initialized point is 1. So I get 1.1. So my next iteration, right, for step 1 is 0.1 and 1.1. Okay, because my xn is counting up by 0.1 each time. 0.1, then 0.2, 0.3, 0.4 to 0.5. Right? So at step 1, 0.1, 1.1, right? So that's my first step approximation. Okay, so I'm going to do the same thing. I'm going to take these 2 points, I'm going to plug them into the equation for my slope fields, right, or just my DE period. So y plus x times y for my points, and we saw before we get out 1.21. Okay, now I take my previous output, or the output step that I'm at, and I add to that my step size times my slope, right? So that's going to be 1.1 plus my step size times the slope I just computed, and I get 1.221, right? So now I'm on the second step, right? I have an approximation at that second step at 0.2 of 1.221. So I'm going to do the same thing. I take these 2 points and I find the slope there, right? Y plus x times y. That gives me this approximate slope at that point. And then now I use this output So notice that I don't have to use my input anymore. I really only need to use the input for calculating the slope at that point, right? So that's nice. So to find my approximation at the third step, I just need to use my previous output and the slope at that output to find the next output, right? So y, my current y, plus my step size times the slope at that y will give me the next approximation, right? And so it's very, very formulaic, right? It's an algorithm. So I actually ran out of space because we're trying to keep 9 decimal places of accuracy. And as you can see, I keep growing in my accuracy, right? I have 1, then 2, then 3, then 4, then 5. So then this will be 6, and then 7, and then 8, right? So it keeps growing how many places of accuracy I have, or how many decimal places I have. So I actually ran out of space. I can't do math with everything, so I'm just going to provide the values after this point, right? So at my third step, my approximate value to the solution curve is 1.36752. So when I take these two and I plug it into my equation like I did before, I get out the approximation 1.777776, right? So that's what 246, like I said. So this will have 7 decimal places. Now, that's just the pattern for this equation. It won't always be like that for every equation, right? So when I plug in my current output and the slope at that point, I can get my new approximation at x equals 0.4, which is 1.5452976, right? So again, I got 2, 4, 6, 7 decimals here. Okay, so all I'm saying is that you basically, when you're doing this, you never ever want to round, right? But however, when you show your values, you do want to round when you show them to me, or if you're creating this table. However, when you're doing math, you want to use math on values that have not been rounded. Otherwise, you're going to accumulate a rounding error, which is never something you want to do, right? So here I have my 0.4. I have my value. Okay, when I plug these in, I get this as the slope. So when I use my current output with the slope at that output, I will get my next approximation, which is the approximation at x equals 0.5, right? So that is my approximate value for my solution curve when I plug in 0.5, okay? So our approximation to y of 0.5 is approximately this value, which is nice, okay? So I call that my 5th iterative value, right? That's my 5th approximation, right? So an obvious follow-up question to what we're doing now is, how good is our approximation, right? Because as we said before, if we go back to this picture, I have some error that I'm accumulating here, right? And like I said before, now if you were to have rounded every single time you did this, you'd have a huge error, right? You would be like way down here. So you would increase that error by rounding as you're doing the math. So you never ever round until the very end, okay? So since our d is separable, we can actually find the actual solution like I said before, and we can calculate our error for y5. Now if this was a numerical methods course and we had an equation that we actually couldn't find the solution for, there are ways to approximate how much error we have. We would actually find an upper and a lower bound for the amount of error we've accumulated, right? So we could say, okay, this approximation is good within this tolerance, right? It's within these many decimal places of accuracy, right? So that's for a much higher level course, obviously, but that is something we're able to do, okay? So through separation of variables, we're able to get the solution, y equals x plus 1/2 times x squared. Okay. So at 0.5 in the actual solution, I get this as my actual value, right? So then we can now look at the error. The error is my actual value minus my approximate value, right? Or y of 0.5 minus my y5 approximate value. So when we do this, we get an error of basically around 10%, right? So I got about a little more than a 10% error, close to 11% error in my solution, right? So error allows us to tell if we have an overestimate or an underestimate. Since my error here is positive because I took the actual value and subtracted the approximate, I have an underestimate, right? So if it was negative, then that would be because my approximate value would be above the actual value, so I have an overestimate, right? So since the error here is positive, a positive error means that I have an underestimate, right? The difference is because I'm below, right? So absolute error is really just the same thing, but in absolute value sign, right? So a lot of times when we talk about error, I don't really care if I'm over or under. I just need to know how much I'm off by, right? So absolute error is just the absolute value of our error that we calculated, okay? Relative error is going to be my absolute error over my absolute value of the actual value, okay? So we would have something like this, okay, and that's going to give me a percentage, right? So what percentage am I off by? So I'm off by about 5.7%, right? So this wasn't a 10% error, it's just 10% in value, but this is percentage wise how much I'm off, right? So percentage relative error is just turning this into a percentage, okay? So that's our lecture, but let's go ahead and look at this in GeoGebra, right? So we can kind of explore a little bit. So we'll kind of switch screens here real quick with my magic word, right? Abra, okay? So now we are in GeoGebra, right? So someone else made this app. I didn't make this app. And I just plugged in our equation with our initial condition, right? So 0, 1 is our initial condition, and we're using a step size of 1. So if you notice here, we have a few iterations, okay? They're the same as ours, except that they had to be cut off somewhere, okay? So I don't know how many decimal places of accuracy they actually have inside of the system, but to display, they need to make it nice for us, right? So they actually cut off some values. So if we zoom in here quite a bit, okay? Right, so here now we're looking at the first 5 iterations, right? So 1, 2, 3, 4. Let's maybe try to pull this down a little bit if we can. However, it doesn't let us look at the actual values, right? It does have a table for us, so that's nice. But we can see how we start to diverge, right? And so we can see what the error is between the 5th and the actual value, right? We can look at the slope field inside of the space, and we can see that we are very accurate with the slope field, right? So at each point we're looking at the slope. We can zoom out, play around with this a little bit. If we were to look at a different starting point, for instance, we would have, I guess I gotta zoom out a little bit. We would have a different curve, right? Because our solution curve is different. Now, let's take off the slope field so we don't have too much stuff going on. Let's change the step size, okay? So if we have a larger step size, right, if we're moving further away each time, you can see that our error is terrible, right? We're making more of an error as we go, okay? So here, we can even look at our values, right? 1, 2, 6, 2, 4. So even just looking at 2 and 6, or I guess at looking at 1, right? At a input of 1 and an output of 2, that's very, very far away from the actual value that we have. Now, if we have, let's say, 0.05, we are definitely hugging this curve, and we can see how close, you know, our values are to a better approximation, right? So we had 1, right? So 1, 2, 2, 1 at 2 was our approximation. So what if we did like 1.09, for instance? So we're a little bit more accurate. So you can see how our values are a little bit smaller. So we can, you know, play around with this. If I have a small step size, I'm pretty much on my solution, right? I have to get very, 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 very zoomed in to see that I have some error going on, okay? But a very, very small step size like this, so it took us 4 or 5 steps to get to our approximate value for x is 0.5. Here I would have to do about 50 steps to get there, right? Because 10 steps will get me to 0.1. So to get to 0.5 approximation, I have to do 50 steps, right? So that's a lot of calculating to do. So it's always better. So, we kind of have to weigh our options. What's better? Do we want a better approximation, or do we even have time to make an approximation like that, right? So that's it. Okay, that's our first introduction to numerical methods in this course.